Okay, so today we will continue to look at the tubular joint design. You can see from the picture left side, you see here the welding is made in multiple passes. It might look so small in this diagram, but actually this width depends on the thickness of the plate. Whatever the thickness of the plate, say is 50 mm, you will see that basically from here to here maybe 70 mm and then another 70 mm. So, it is quite a large size area where you need to do the welding. When you try to do this, you normally do it using multi-pass, means every time you use a 6 mm or 8 mm welding rod, you weld around first pass, second pass, third pass. So, you will see that several passes you have to go through in order to make sure that you get the complete filling. And the reason why we need to know this, the particular purpose is the profile of the welding. You see at the surface, if you actually have I might show in one of the class a real photograph of welded surfaces, you will see a lot of changes in the curvature. So, when it is getting adjoined to this connection between the base metal to the weld, you may not get a very nice clean surface, and that is where most of the time we see the stresses increasing because of the notch effect. We will see from one of the finite element picture later on. I think you might be seeing here, you can see that the change in stress at that location could be substantially larger, and that is the reason why we need to know. So, we will come back to this picture later. Basically, the reason why we need to know how it is welded is just to understand how the distribution of stresses at the location of the welding, and that makes the difference, because that stress is larger than stresses applied at the plate elsewhere. Basically that is the reason why we need to know. Now, if you look at the total process of application of load from brace to card, you could see here in these two diagrams, any one of them can happen. So, the first one is basically a local bending of a cell. Imagine if you have the brace wall thickness is substantially larger, good, strong, and you apply the load, what will happen is basically just poking at a thin cell. If the card diameter is large, wall thickness is smaller, what will happen? It is just going to go down, something very similar to a local bending of plate, and probably if the shear capacity is not adequate, what will happen? Simply shear through and the brace can enter into the card member. So, that is basically starting with the local cell bending. It may actually end up punching through, piercing through the card if the card thickness is very small. So, now you can see one parameter we have identified, the thickness of the card is going to play a major role whether it will fail or not fail, is not it, and association with the diameter. See, you cannot isolate a thickness and say whether it is too small or too big, all depends on what slenderness of the section itself. So, larger the diameter, this bigger thickness also become slender, smaller the diameter, smaller thickness also can become very stiff. So, the d by t ratio is an important parameter rather than just the wall thickness, the diameter to the thickness. If you look at the right side, because we made the wall thickness maybe better, thicker, you can see instead of locally failing, overall pipe is getting ovalized. So, something similar to a ellipse. So, that also can happen depending on relative stiffness of the brace and the card. So, what we need to understand now, the total problem may be not isolated only to the card or only to the brace, it depends on the relative stiffness of the brace member and the card member, and that is what we are going to just look at one by one. And when you do this kind of bending, for example, you have a load here, you have a bending like this. So, you will see that the bending moment will develop locally, and you may have a local bending stress, which can actually substantially be larger than the actual stress produced by this load itself, because we made the plate thickness so small. So, it is basically bending here, and that is the kind of information we are actually looking at. Now, if you look at this, yesterday we discussed about the design approach is from 3 dimension to a planar information. We are trying to go for plane by plane, and in each plane you can look at any connection, they will fall any one of these characteristics. Either it can look like a T junction, it can look like a Y junction, or can look like a 2 Y junction in opposite direction, or can be a direction which is perpendicular to each other, or can be any angle between them which is similar like a X joint. So, what we are trying to understand, any one of these will be fitting into your actual design. Only thing is the parameters may change. For example, when it is 90 degree we call it a T junction, when it is less than 90 degree it can be from any angle from lowermost as like say 30 degrees, 40 degrees up to 90 degrees. So, if it is within this, you will call it a Y junction, because it's look almost like a shape of a Y, whereas when it becomes 90 degree it is T junction. And if you have 2 or 3 members coming in, for example, in this case I have drawn only a two member coming in, which we call it double Y, or we can call it K junction. Now, there is a primary criteria for a K junction, which we will see little later, because just at a look at it we are just classifying based on geometry, whereas it is not going to behave similar like a K. K means what? It is only shape, but the behavior we have to look at the load transfer. So, you can see here, you go and do your design, or anybody does the design, almost every one of them will fall into any one of this category, which we will see one by one. Now, what is called a K junction or K connection, what is defined as is basically a balancing of loads. For any joint to be in equilibrium like this, then you have two members, one member is having a tensile load, another member is compression load, then it is called a balanced K junction. So, as long as you have this balancing, if whatever the load comes here and taken by the other brace, angle of this and angle of this is same, then there is no load applied on the cord across the section. So, there is no shear load, because member load coming in, member load goes out. So, that means it is balanced. So, this balanced junction is always better, because the local stresses will be counterbalanced, one is compressive, the other one is tensile. So, that is why we have a special case where the loads are balanced, then it is called balanced K junction, or you have T or Y, there is no balancing here, whatever the load is coming from the brace have to be taken as a beam shear by the cord member. So, here there will be substantial increase in stresses compared to the K junction. So, when we do practice using design, we will compare, use the case of balanced K equation and use a Y junction, and find out the result will be more for this compared to K. So, that is the idea that we want to. So, when you are trying to classify, you need to see not only the shape, but also the whether the load is balancing or not. For example, you have both equal loads, you can classify as a K joint, but if one of them getting more load, another one is getting lesser load. So, you can see that there will be fraction of K joint plus fraction of unbalanced Y joint, is not it. So, that is what the classification, we call it load path dependent classification. Not only the geometry how it looks, but also you should look at whether the load is balanced or unbalanced. So, for classifying into K junction, we need to have the loads are balanced. For T and Y, you do not need to have the load balancing. X connection, anyway you can have any type of combination, but of course, you can have both braces carrying compression or both carrying tension, whichever you will have to have two different design equations, and many of the time we have this type of connections. So, now you can see, just carefully watch these three diagrams. The first diagram, the diameter of the brace is smaller, quite smaller, comparatively smaller to the cord diameter. I think most of you understand now the cord and the brace, no. So, basically the receiving member versus the member transferring the load. So, the blue color is the cord member receiving load from this brace member. Now, you see the diameters, I purposely made it to just indicate how things will go wrong or how complicated things could be. You could see here is smaller. So, basically the ratio becomes less than half or equal to half or whatever, and when you make the brace bigger and bigger, see here the D by D ratios, this is must be the other way, basically D by and this also. So, when you have the D by D ratio close to 0.8, you can see almost they look almost similar, is not it. When you come to the right side, when they become equal, you can see the brace connection is coming all the way up to the middle of the cord member. So, you need to realize how this will be done, because this will be a singular point, both diameters are same, and welding here becomes actually impossible, and that is why we do not want to have any brace member as big as the cord member. Try to limit less than 0.9, 0.8, and when you have such a situation, you actually have the stress concentration here will be very large because of the welding singularity. So, you need to understand the configuration when before designing whether you should go this way or the other way, the results could be different. Just to indicate what is the increased stress at the junction, I just wanted to show you basically just a flat plate 50 mm by 200 mm welded to another 50 mm, just a plain plate, it is not a 3-dimensional plate. So, a load is applied in terms of pressure at the top about 100 megapascal. So, all the plate around all the way up to this point you can see is stressed equally, because there is no change in direction, there is no change in dimension, there is no change in any local pattern. So, you can see uniformly applied axial stress on the plate from top all the way up here, but when it comes to a junction you can see here the local change in direction from a vertical plate to a horizontal plate, you can see a notch stress, basically we call it a notch effect, and that becomes a highly stressed point. Now, if you look at the stress difference between this is I applied a 100 megapascal, and when you apply to this location you could see almost 250 something around. So, is one location here the dimension of this area is about say maybe 5 mm maximum to 10 mm, in that vicinity you can see the stress is 250, 2.5 times the applied stress. But can we conclude based on this assembly will fail? Definitely will not fail, because it is only if you see everywhere the whole area throughout the next section here, if it is 250 megapascal, probably we can conclude the section is highly stressed trying to over stress and fail. But fortunately only two junctions, left side junction and the right side junction is only a local 10 mm plus 10 mm, but still substantial cross section is under stressed, because you see here the stress at this location is around probably 110, 112, because it is blue and green mixed. So, still it will take a larger stress before the failure takes place, and that is what we need to understand. These local hotspot stresses or local stresses are only isolated for one location, not throughout, and if you understand that concept, that means this junction or this connection is not going to fail right now until you increase the stress in such a way that the whole neck will become 250 or 300 megapascal. So, yielding will start, and that is the idea behind. We need to worry about hotspot, but actually we should not unduly worried, because the hotspot is not going to be or throughout the section, and that is why it is called hotspot. It is basically a isolated points on the connection. A similar exercise can be looked at on a pipe to pipe connection. Just looking at it, you can see a typical pattern, because in this case it is not a flat plate, it is a hollow circular section welded with another hollow circular section. So, you could see here on that particular location is very high stress of 200 plus, but same 100 megapascal only I have applied at the top. Most part of it is green, basically there is no change, no deviation in the load, no change in the cross section, and it comes, but when it comes to the connection at this point, it is reflected on two sides, reflected on the brace and reflected on the cord. So, if you go back to this picture also, you can see here this junction, some portion of the vertical plate is stressed, some portion of the horizontal plate also stressed. So, it has got effect on both sides, and that is why we need to know what is the pattern of stress in the cord side and what is the pattern of the. So, if you go actually, if you zoom this area very large zoom, you will find that there is the plate horizontal and plate vertical coming and joining. You will see that the stress on the vertical and the stress on the horizontal, there will be different magnitude, but they will be matching at the intersection. If it is not matching, they probably failed, that means they have separated. So, in order to see that, you need to go to the software. I purposely could not put it here, but you can see that there will be a connected plate stressed in a different manner. So, what we understand from here, when I apply 100 megapascal at the top of the brace, which is basically nothing but load divided by your area, because you know the load on the member, you divide by the area, you got 100 megapascal, which has become 200 something megapascal at the junction, purely because of the change in geometry. From a vertical pipe it becomes a horizontal pipe carrying the load. So, that is called hotspot stress or stress concentration, several terms we can use, basically nothing but the stress produced here, the 207 is not uniform throughout, it is going to be maximum one place and lesser elsewhere. This is what we were discussing about the methodology. I think the idea is clear. We could not do the design in 3 dimensional multiplanar joints. So, what we are going to see is develop a parametric equation empirical method for each of the plane frame, and basically looking similar to either t, y, k or x, and analysis will be done plane by plane. Of course, the 3 dimensional effect is taken into account in terms of empirical multiplications. So, you do the design of one side, but that effect of other side is already taken into account. So, that is the idea behind all those empirical equations, and basically you repeat the procedure for all frames in one junction and look at whichever is producing maximum requirement, that will be the design. For example, if I have one jacket leg, one member is coming in this direction and another member is coming in the perpendicular direction, you will do the design of one member first, find out what is the thickness required, keep it one side, go to the next frame plane, do the design, find out the thickness, whichever is asking for highest thickness, that will be the design requirement. It is not that you will take thickness from here and thickness from other, add it together, it is not like this. The cross reference effect is taken into the design itself. So, you do not need to worry which is going to be. So, that is the methodology adopted in the tubular joint design. Now, you see here this is what we were trying to discuss earlier also. If you look at this picture, the first yield is the most important. If you look at the load deflection diagram of a typical tubular joint, either T junction or Y junction, the first time when you keep on increasing the load, when you see a hot spot, that hot spot is one location, maybe 2 locations, the joint is not going to fail, and you further increase the load until such time crack develops at one point. Very similar to the discussion we had on the plastic collapse analysis, basically you keep on increasing the load until such time the hot spots will start increasing from one location to multiple locations. Basically one location yielding, load is transferred to the next point and next point, next point. So, you will see that basically a cracking will happen after sufficient amount of load has been applied, but one small crack does not fail. So, you need, for a failure to happen, you need to have dislocation of the brace and cord for a sufficient length. 1 millimeter is not going to fail. So, if it is 20, 30, 50 all around the circumferences. So, that means the failure will occur when the load is substantially larger. So, from the time that we saw first yield or so called the hot spot at one location to a failure, you will see that the amount of load that you have to increase to fail that junction is typically 6 to 8 times or even 10 times sometimes. That means, if you have 100 kilonewton applied on this, it will only fail at 800 kilonewton. That means, the redundancy exists in this type of connections. Now, we have to decide whether we want to do the design as per 0.6 or 60% of yield, like normally we have designed the members, 0.6 as our allowable stress factor, which I think most of you remember for bending, axial and shear and so on. We need to decide whether we want to use that kind of concept or we want to go beyond. Now, nobody will accept a design when the design itself says I will have a crack, is not it? I think no one will accept. So, you can actually have a condition not acceptable if there is a crack in the design calculations. So, what we are trying to find out whether we want to go below yield or slightly higher than yield. The concept adopted by API is basically between the yield and the crack, because the first crack may happen at say 500 kilonewton instead of first yield at 100 kilonewton. So, there is a substantial margin between 100 and 500. So, let me use 200 maybe, still crack is not there, but other points have yielding which is acceptable, but still a lot of redundancy is there. So, the idea behind the tubular joint design, we are not using the elastic concept, we are going to use the elastoplastic or so called ultimate strength concept. The ultimate strength basically just below first crack. We do not want to have crack, but we want to have higher strength than the first yield. So, that is the idea behind, divided by a factor of safety, and basically that is the idea of almost all the codes behind the tubular connections. So, we need to find out what is that ultimate strength. You look at this picture here, in this picture, under the elastic stress. What is the meaning of elastic stress? If you remove the load, what will happen? The shape should come back to original circular shape. Now you look at just beyond yield, there may be a permanent deformation, could be larger, could be smaller, depending on where you are. If you are very close to the yield, maybe you will not see this distorted shape, but if you are close to somewhere here, you will see that this distorted shape will become permanently, which is also not good. But if you go beyond the first crack, you may see that the connection becomes disjointed, that means the brace will come separately and the card will become damaged. So basically we want to go between this, and with the proper factor of safety, we do not want to have permanent deformation, we do not want to have a crack, but we also do not want to design below yield limit, because the capacity is very small, and that is exactly the idea. We go beyond yield. Yield means one location, hot spot, not yield everywhere. Whereas if you actually take a piece of plate like this, you apply tensile stress, yielding will be uniform across, isn't it? Because when you apply 300 megapascal on either side, the stress along this section everywhere will be 300. So basically that is not permitted. Whereas why we are permitting here beyond yield is because it's only one location is yielded. We have so many other connections far less than the yield point, and that you must remember, because you can't get an idea that we will allow yielding in joint design, but not allow in member design. The reason why we are allowing is because of non-uniform state of stress along the periphery of the connection, and one point is higher, the other points are very low stress. So we want to utilize the reserve strength available, so that we can optimize the connections. Typically back in 1990s, early 80s and 90s, many research was carried out on this type of joints by doing experimental test. So you fabricate a T joint, go to the testing machine. I think most of you might have seen the universal testing machine. So you can put it there, apply load, keep increasing in increments, and just find out what is the load at which the junction has failed, either by collapse or by pull out. So both tests you can carry out, and basically you see this diagram, what you see here is horizontal axis is gamma. See, gamma is the ratio of d by t of the chord, very important parameter. The two cylinder you make is going to fail definitely, and the vertical axis is the failure, the relative punching shear stress at which the failure occurs. Quite a lot of experiments were done as usual, and you can see they have drawn a line just at the bottom of the whole experiments, and described by this curve. Basically you can write a equation using a regression analysis and find out what will be the equation for future use. So this is how almost until 90s quite a number of experiments were done, but after 90s what happened, the experiments have become quite expensive. So what was done during 90s to 2005, quite a lot of finite element studies, like what you have seen, this kind of analysis, provided your tool is validated. That means you will do one experiment, compare with your finite element analysis, make sure your parameters are right, then you go for several finite element analysis instead of spending a lot of money and time on doing experiments. So that is the idea behind. Over a period of time, lots and lots of such publications have come. So API had a committee in 2001 to 2004, committee of researchers put together and collected all the study work from 1970s until 2000, and they came up with a new design code. This is actually old design code, which I am not going to speak about it because it is becoming obsolete. It's until 2002 we were using this method, but they found that this is not really conservative. So that is why the committee was set up to make sure that they collect all the information from the recent past and they come up with a new design equation, and that is what we are going to see. Basically parametric equation, you should understand nothing but the equations are simple polynomials. I think most of you also can do experiment in our laboratory. You can fit a polynomial equation to describe the behavior between the result and a parent variable. Parent variable could be diameter, wall thickness, angle, length, any more than one or one itself. So basically the result will be your response of the structure in terms of deflection, in terms of capacity to failure. So, that will be your goal. So, if you relate the response versus the parent variable by some means, some relationship, not necessary that you should derive it. Basically in mechanics you normally derive. For example, a bending capacity of beam, you do not write yourself, you actually derive from first principle of simple bending theory. If it is actually loaded, you derive, whereas in this particular case we can't derive because the behavior is so complex. So, it is purely based on experimental studies, and the relationship between the capacity and the parent variable is by, I would say, simple interpolation. You do 2 experiments, so in between maybe it might behave similar manner. So, that is called a parametric equation, which is nothing but a semi empirical idea. So, what will be the failure criteria? We do not want to have a situation where you have a local chord failure, something like this. You see here, this chord is not just a limited length, it is continuous connected to other parts of the structure. So, you could actually have a failure like this because the chord is having sufficient stiffness, but locally is failing, something similar like a beam. You can see here is actually both ends supported and the middle is going down, just like a small span beam. So, reaching elastic limit of the material is one of the goal that we want to see, but we want to go slightly higher than that, and material yield, and then the first cracking and the load at which is what we saw in that. So, we need to have test or FEM simulated until this. So, you can't do a finite element analysis in elastic state and take the result and use it, which is not correct. We need to do a finite element analysis until the failure occurs and then note down the capacity until first crack. So, it is a substantial computational power required. Normally, if you do a static analysis, it may be faster, but when you want to do this kind of elastoplastic stage analysis, you may take longer time. So, what are the failure modes we are expecting? We think it may be happening in this way. There are 4 discrete probability that any one of them will be causing the problem. One is the general collapse, second one is the local failure, which we saw earlier, and then the third one is unzipping. Basically, one location is failing and that location there is no contact, load is going to the next 2 locations around, and that location get overstressed and opening up. So, if you have a one location opening or a crack or a separation, the load from that part will go to the next part, and subsequently the opening becomes larger and larger and becomes disconnected or disjointed. The last one is the material problem, which we discussed about it during earlier few days. Basically during welding you heat the material and you make a fusion bonding, and that may actually give up because of the irregularities there. So, we need to see what exactly is the remedy that we can make, because this we can prevent definitely by selecting suitable material, whereas the first 3 we have to design for it in such a way that that does not happen. So, general collapse is something like this. One of the member is getting compression load, the other member is getting tension load. So, you can see a rotational behavior about the common point, which actually can ovalize as well bulge and buckling effect at the location there. The local failure of the chord is basically because of the pull out, because the d by t is so small, just coming out. When it is coming out, it is actually taking part of the chord itself, it is actually a punching pull out. The third one is the unzipping, is nothing but very simple idea, smaller yielding, smaller crack, the cracked portion load is transferred to the next point and continuously progressive unzipping happens. This may happen if you have one particular location not welded properly or defective welding, and that is the location the load cannot take, whereas you have actually taken full area for your load calculation, whereas actually some locations are not possible to transfer, and this progressive failure can easily happen in any type of connection. Last one, basically the material problem. Now, the material, one important aspect we have to see in this connection, always remember when you try to weld a plate perpendicular to the plate surface, when you try to pull out, what will happen? Across the thickness the load is applied. Normally the plate is very strong when the load is applied along the length or width direction, the plate has got grind direction aligned in the plate length or width. Now, you apply load across, that means the skin is trying to come out, that means the plate characteristics should be such that you should have enough strength in your crystalline structure that they are not going to come out. So, that means we have to go back to the parent material, whether the material characteristics is able to transfer the load across the thickness or not. Otherwise, what will happen? Something similar to your plywood, it will start coming out. You imagine you take one plywood, layers of material, and try to apply the loading across the thickness, it will straight away the first layer will come out, isn't it? So, that is exactly the bonding is required between the grind structure, and this can actually happen in any material, and specifically for steel it may actually happen when the thickness is larger and larger. For example, 10 mm less susceptibility to come out, whereas 50 mm the chance of peeling off is more, and that we call it lamellar tearing. Basically the plate comes out, instead of coming out together, something similar. If it will be, if it comes out like this is not anymore a material problem, it is actually a local wall thickness problem, not enough, so it is coming out. Whereas here you see this picture, wall thickness is still adequate, but unfortunately the material has degraded for several reasons. One of the reason could be the heat affected zone. Basically at that location, when you are welding, you are increasing the temperature to 1000 degrees. So, that time material characteristics deform and get weakened, and basically cooling is faster than what the necessity. For example, whenever you are doing welding 1000 degrees, and you should not cool it very quick, it should be slow cooling. If it is quicker, then you will have a brittleness form and can actually crack even immediately after welding. So, the heat affected zone is one of the potential problem where we have a worry about, and also the failure may happen due to fatigue. I think that is what we normally do. We want to break something, you apply the load or you apply the similar thing several times repeatedly, so it may come out or break. So, in order to avoid this, we need to select a suitable material. Number one, it should be homogeneous across the thickness. I think you understand the word homogeneous, that means there is no impurity or voids or crack within the thickness across. So, when the load is applied, it should not come out. So, that special material we need to buy, because only for that location, not for everywhere, because at the connection we will buy a special material which we call it through thickness property. That means the property across the thickness is same, and when the loading is applied, the grind bonding is such that the lamellar tearing will not happen. So, that material sometimes is noted as JUT 35, or we call it JUT property, because across the thickness is called a JUT property. Length and width direction anyway you will have, and that means the notation what we normally give is that 35 means 35% elongation across thickness. So, how do we do it? Actually, most of you might have seen a UTM machine, you have seen or not seen? Okay. So, you might have seen the tensile testing specimen. It will be a small rod with the attachment pieces at, and you just do a tensile testing. So, you take the same tensile specimen testing and cut the specimen into two half. At the middle you cut a plate, for example, this is the plate, you cut one circular plate of 10 mm diameter, and basically in the tensile specimen you fit it in between and again pull it. So, you are pulling actually across the thickness, and when you pull it before failure, if 35% elongation happens, for example, I took only a 10 mm thick plate. So, it should become 135% or basically 13.5 mm it is elongated, then it has got 35% elongation before the neck form and failure, because you keep on pulling, then there will be a neck formation and just break out. So, that means the more the percentage like this is better, because if it fails in 5% deformation, that means it is not very good. So, we need to see that when you apply the loading across, it should take ductile failure rather than brittle failure. Suppose if you have a some kind of voids inside the thickness, when you pull it, it may actually come out straight away, there is no deformation, and that is what we were trying to prevent. So, that notation is called a JUT material, because it has got a JUT property or thickness property, which makes the load transfer without failure. You will see that in that this kind of picture I have given you some kind of You see here there is a special color, green color there. Basically only at the junctions we provide such material, so that the connections become safe. So, what are the codes available, and basically these compact connections we will discuss later. What are the codes available is basically nowadays ISO, API and also DNV codes, but the originator of this whole business is actually coming from American Welding Society. Actually even before API was set up, this American Welding Society has come up with the design requirements in an informal way, because that society is not meant for offshore business, but they have been using non-circular tubes, for example like a box sections, rectangular sections, hollow sections used for various building industry, and that is why they wanted to develop such a connection, and basically that from there it originated, and subsequent editions of AWS they have introduced circular sections. In case some places you can see in many of the airports circular hollow sections are also used, and then later it was adapted by, this was adapted by the API codes and copied and modified, and almost all the work is coming from this P.W. Marshall. He is one of the pioneer. He has done extensive work on tubular connections, and he is still alive. He has been doing some more and more publications. He is member of the API subcommittee for structures, and most of his work was adapted in the earlier revision. But what happened is, unfortunately his work was based on early part of some small scale experiments plus some finite element analysis, proved to be not conservative, and rather right now we are not using his proposals or his equations because found to be not very good, and over the period of time more and more data was collected, more and more experiments were conducted, and the new equations will be not looking like what he proposed earlier. So, basically he has done some work. Now, we will just look at the classification of joints based on loads. I think very interesting. You should understand that it may become Y joint or it may become K joint depending on whether the load is coming balanced or not balanced. So, if you look at that, we call it load path dependent classification. So, you should not just believe the joint looks like a Y joint, I will go for Y. It should not be that way. You look at geometry plus the loads coming in. The only simple idea is, if it is balanced it will automatically go to K joint, if it is unbalanced it will either go to T or Y joint. So, simple classification idea you see here, I have got a brace 1 and brace 2, one is carrying compression load brace 1, the other one is carrying tension load, different magnitude, but then we just find out what is the vertical component or component normal to the brace chord. You should not call it vertical or horizontal, normal to the chord. So, this is basically 90 degrees, so it is normal to the chord, and this basically an angle. I will find out what is the normal component. Now, if this P1 and P2V are equal, then I can call it K joint because its load is balanced, even though they do not look like a K geometry, because there is one member is vertical, the other member is slightly inclined, does not. So, you may not classify as a K joint, but fortunately the loads are balanced. Now, you may not get exactly same load, nobody is able to control the load. So, you may get different magnitude. So, if you look at this vertical component or normal component equal to P1, then both members, this member and this member will come under the classification of K joint. Now, if they are unequal, that is where the problem, because even after finding out the normal component, if P2V is larger or P1 may be larger. So, we have got two classes. In first one, P1 is greater than P2V, P1 is larger, P2V is smaller. So, what we will do is, we will find out what is the amount it is balanced. For example, if this is 200 kilonewton, this is 300 kilonewton, 200 kilonewton is balanced, only the remainder 100 kilonewton is not balanced or unbalanced. So, we would say out of 300, 200 is balanced, that means we can find out 200 by 300, 66% behavior as K joint for both the braces, but for P1 because it is slightly larger 100 kilonewton. So, 33% is T joint. You understand the idea, no? So, we just simply split the problem into two different ideas. So, vice versa also can happen. You see here P1 is less than P2V. So, automatically what will happen, whichever is satisfying that much portion is balanced, the remainder portion is unbalanced. So, this is how the joints have to be classified depending on whether the loads are balanced or not balanced. We will have some few cases. If you have understood, if you have not understood, then let us stop now, because you will have to classify a joint and design yourself in the exam. So, basically first idea, normal components of braces, if they are balanced each other, then it is called balanced. If any one of them is larger, the larger one you take it, split into two half, balancing part and non-balancing part. Balancing part, the ratio is so many percentage of balanced K joint, the remainder part divided by the overall load or bigger load will be unbalanced part. It can be T or it can be Y. In this first case, it became balanced part is T joint, the second one balanced part is Y joint. So, you should do this one before going and designing. So, you cannot get just fooled by how the joint looks like. It can be looking not like K, but we will classify into K joint. So, you need to do some practice, probably I will give you one of the example one of the days. So, we have got some 9 cases just to illustrate how things are done. So, I will just explain one or two, then you can just follow the notes. So, if you look at the first one, very similar to what we described just now, the brace 1 is carrying 1000 kilonewton, brace 2 is carrying 1400 opposite. So, basically in this one, if you just look at it, I have just taken as 46 degrees, which will be basically 1400. If you find out the normal component, what will happen? You will get around 1002, 1003. So, 1000 and 1000 they get cancelled each other. So, this can be classified as 100% K. You understand the idea, no? Now, if I have this angle instead of 46 degrees, I have 25 degrees or 30 degrees, then you will not get 100% K joint. You need to find out what is the load amount here, and that amount only will be K joint. The remainder here there will be a T joint of certain percentage. So, you should know how to calculate. So, same thing here, if you come to the second, I have 1400 applied only on this brace does not carry any load. So, here I do not have a balancing load, it is unbalanced load fully. So, this will be 100% Y joint, there is no K behavior, because there is this member is carrying no load. So, that means I can't go to a K. And coming to the last one, you see here exactly that is what we were trying to talk about, 500 is there, but I will get 1000 from there. So, basically 50% K joint for this, because that is the one higher, is not it, because that 1000 is going out, 500 will be balanced by this. So, this and this 50% K, whereas the Y joint additional 50% will come, because that is carrying more load. So, very simple algebraic comparison. So, like this there are quite a few examples I have just given from API. So, you should understand, try to, I will ask the girl to give the notes today, try to practice. So, the next one I do not think we need to go through, because you can easily read it just to get an idea. The next one is the parametric equations are developed based on 3 parameters. One is the diameter ratio, as I think I have explained to you the importance of diameter ratio. If the diameter ratio is very close to 1, you see a problem there. And similarly, the slenderness ratio of the card, diameter to wall thickness. The third one is the wall thickness ratio of brace and card. These 3 parameters, plus you will have the angle as one of the major parameter to differentiate between K, Y and T joint. And basically with these parameters, if somebody can come up with the equation to describe this is the capacity, that will be the best. So, basic idea is what are the parameters range is permitted, is just summarized. I mentioned it in the last class. You cannot go beyond these limits. Basically, if it is going beyond, the equations are not valid, because most of the text and finite element studies done within these ranges. For example, beta, beta is basically between 0.2 to 1, and the gamma is between 10 and 50, and the theta between 30 and 90, and the yield stress should be less than 500, and the gap basically should be greater than minus 0.6, that means you should not have overlap. So, these are the parameters they have used to study the experiments and the finite element and come up with the empirical equation. So, if you are outside here, there are some guidelines given here, calculation using actual geometric parameters, do that exercise, calculate based on the limiting. For example, if the angle is 28 degrees, you have to do two calculations, do the calculation using 30 degrees, do the calculation using 28 degrees, whichever gives you the lowest capacity, you use that capacity as the design capacity. So, that is the practice. It is not that if you go outside, you will not be able to design, you will be able to design, but with a lower capacity. I think we will see this tomorrow.